Okay, so we're going to have a think about magnetic fields. Now I guess we're pretty familiar with the idea of what a magnet is. A small metal bar, piece of iron or steel, which when it's been magnetised has an effect on other magnetic substances around it, which can, for example, deflect a compass needle. But the power of magnetism seems in some ways magical, mysterious. How can it be that a magnet can affect things even though it's not touching them? Well, the answer to that question is that around a magnet there is what we call a magnetic field. And as you probably know, you can detect the pattern of the magnetic field by sprinkling iron filings on a piece of paper above a magnet, or perhaps by taking a compass and moving it slowly from a north pole of a magnet towards the south pole. And if you did that, each time moving the compass so that the needle points in a consistent direction like this, what you'll find is that the direction of the compass gives you an indication of what we call the direction of the magnetic field. And as you can see, it goes around in a loop from north to south. And we call that line a magnetic field line. And if you were to plot a few of those, starting your compass at slightly different points, you'd end up with a diagram which indicates the shape of the magnetic field around your bar magnet. And as you probably know, what that will end up looking like is a little bit like this. If we have a north pole there, a south pole there, we'll have some field lines which come from inside the magnet, like that, from north to south. We'll have some field lines coming out of the ends, this. And then we'll have some field lines curving off into space like that. And perhaps one or two more around here. And I could draw another one up here maybe. Okay. Now notice a few things about the diagram. First of all, the magnetic field lines are flowing in a particular direction. So magnetic field lines have a direction to them. The direction is indicated by where a compass would point if you put a compass at any particular spot. If I were to put a compass here, the north pole of the compass would point that way. We typically use the north pole, and therefore the arrows are to indicate directions of magnetic field lines go from north and around to south. This diagram is in some ways misleading because it makes you think that the field lines have just stopped. They don't actually stop. Magnetic field lines are always complete loops. It's just that as they get further and further away from the magnet, they become, the magnetic field gets weaker and weaker, and it's harder to actually detect where the line should be. But nearby you can see we've got loop-like lines there. So the arrows indicate something about the direction that a compass would point if you were to put it there, away from north, round towards south. Something else you notice as well, which is that if you look at the ends of the bar magnet, you can see that at those points the field lines are most concentrated. There's more field lines in a given area around about here than there is, say, out here. And that tells us something about the strength of the magnetic field. The magnetic field strength is greatest when the field lines are closest together. And as I'm sure you know, the strongest part of the magnetic field given by a bar magnet is around about the poles. So we can see that by the density of the field lines, how close they are together. So that's what we get if we had a simple bar magnet. Now what happens if we put two bar magnets together? Well, depends how we do it really. If we put two poles together at the same kind, then it's almost as though the field lines themselves repel magnetically. So suppose I had a north pole there and a north pole here, then the field lines sort of push each other out, and we get much less of a magnetic field. In fact, we'll have a region in here where there's really no magnetic field at all. So the field lines are pushing themselves outwards like that, and as you can see, we're left with a region in the middle here with no magnetic field. So that's what would happen if I had a north next to a north. What about north next to south? If we put north and south together, then the magnetic field lines reinforce in the middle, and we end up with a really strong magnetic field in the middle there. A little bit of curvature around the edges as the field starts to leak outwards. So we're going to get something a bit like that in between the north and the south. Probably some field lines curving out here, weaker as well. Oops, put that one in the right direction, from north to south. Now notice something about here, that here the field lines are about equally spaced. And I said a moment ago that the spacing of the field lines tells us something about the strength of the magnetic field. So if the field lines are equally spaced, that's telling us that we have a magnetic field of constant strength, what we call a uniform magnetic field. A uniform magnetic field, one where as you move from the north to the south, the magnetism stays approximately the same intensity, the same strength. So just remember that between the north and south pole we're going to get a uniform magnetic field. So that's something about the magnetic field patterns for bar magnets. In the next video we'll look at what happens when we use electromagnets.